Hello, and welcome to the fourth and final lecture video for Chapter 4 from the Cosmic Perspective, ninth edition. In the previous three videos, we covered sections 4.1, 4.2, and 4.3 respectively, all a background in mechanical understanding of the universe using the language of physics, motion, energy, all of that, the laws of motion. Okay, so now in this final video, we're going to cover two sections, section 4.4 and 4.5. We're going to talk about the universal law of gravitation, and then in the next section, talk about some of the implications of gravitation. Okay, so let's get right to it. What is our goal for learning in this video? Well, the first question, what determines the strength of gravity? How do you actually find it, right? How do you know that the strength of gravity is greater somewhere than somewhere else? I keep talking about in previous videos how you're lighter on the moon than on Earth. Why is that? And how does Newton's law of gravity extend Kepler's laws? Okay, in particular, Kepler's third law, because we can make it really useful by combining it with Newton's laws. Okay, so the universal law of gravitation is the following. Okay, so as a series of statements, we'll start with statement one. Every mass attracts other mass. Okay, so it's a fundamental idea that mass is attracted to other mass. It's just a property of mass. Okay, kind of like there are properties of charges. There's negative and positive charges, and there's some story there. For mass, it's just always attractive. Everything's pulling on everything else. The sun pulls on the earth pulls back on the sun, right? The sun's a lot larger, so the sun doesn't move as much, but everything pulls on everything. Okay, now, second part, the attraction is directly proportional to the product of their masses. So two large objects will pull with a lot of force, two smaller objects will pull from much less force because it's the product of the two things that are pulling on each other. If there's one really big mass involved, then the product will probably be, will potentially be larger. But, if you take a really big number, like the mass of the Earth, 10 to the 24 kilograms, and multiply it by a small number, well, then, you can still end up with a relatively small force if that small m is small enough. And finally, the third statement, attraction is inversely proportional to the square of the distance between their centers. Inversely proportional just means something's in the denominator, and the square means that if you double the distance, you get a quarter of the force because that's it's inverse, so it's in the denominator. Doubling 2 gives you 4, so it's 1/4. Okay, that's what that statement means. Inversely proportional to the square. Okay, so you put it all together, you get the universal law of gravitation, and here it is as a formula showing the system, right? The parts that actually are interacting here. These are the two masses. These could be two moons or worlds or stars, okay? They could be anything, right? And on the microscopic scale, there's lots of things too, okay? Particles, right? M1 and M2, M per mass, okay? They are some distance apart. Obviously, in astronomy, a lot of the distances we care about will be orbital distances, like the radii of orbit. Okay, now the formula you can see has the product of those two masses, just as we said in number 2, and then in the denominator, it's got the distance squared. So, it's inverse, so it's in the denominator. The only thing we haven't mentioned that is beyond the statements, beyond the concept, that makes the formula numerically correct and have the correct units is this constant right here, okay? This constant is called the gravitational constant, and it is a experimentally determined constant that seems to be fundamental to the universe and is one of a very small select group of fundamental concepts or fundamental constants. All right, the fifth thought question of the chapter. If the distance between two masses is doubled, the gravitational force between the two masses is what? Remember that inverse square relationship, okay? Option A increases by a factor of 2, decreases by a factor of 2, increases by a factor of 4 on C, decreases by a factor of 4 on D, and finally does not change at all. Which is it? So you got lots of options, 2s and 4s, increases and decreases. Okay, what is your answer? Hopefully you've had enough time. Decreases by a factor of 4. So if R goes to 2R, then the force between them, okay, the gravitational force is going to go to 1/4. All right, so it's going to get cut by a fourth. Why? Because remember, the force is proportional to 1 over the square of the distance. There you go. Okay, so Kepler's laws apply to all orbiting objects, not just planets, okay? That was Newton's realization, right? This isn't just a system that just only works for our sun and the planets that orbit the sun. It also works for the moons that orbit Jupiter, for example, or it certainly works for the planets that orbit other stars, although that wouldn't come until much later, much after Newton's life, that other planets or planets around other stars were confirmed to exist. But the idea was that it has to be a universal law, okay? Furthermore, ellipses are not the only orbital paths that an object can take. So that means that we can have unbound orbits, parabolic and hyperbolic orbits, basically flybys. You can have an object swing by a gravitational pull, but not actually go completely into it. We see this for objects that come into our solar system and just pass through. They're difficult to detect, but we've confirmed at least one, which is quite fascinating. And we certainly take advantage of this concept of parabolic unbounded paths when space probes are sent out into our own solar system by organizations like NASA, because they actually fly near a planet taking a parabolic path. Now, they don't get into orbit, right? If that's not their final destination, they just fly by it. So that was one of Newton's realizations, that there's more to it. It's a fuller body of calculations, and it's also a more fundamental law, more fundamental than Kepler realized. Okay? Now, another important concept with gravity and the universal law of gravitation is the concept of the center of mass. I mentioned this briefly, and I don't understand that maybe no one knew what I was talking about when I said that, oh, there's a center of mass of a system, because sometimes it doesn't matter. For example, it's very safe to assume that Earth orbits the sun, and we just kind of assume, well, that's probably the center of the sun, right? Well, technically, it's not, because Earth is massive, right? 1 millionth the mass of the sun approximately, but it does have some effect. So that means that you need a balance point between the much more massive sun and the Earth. That balance point is called the center of mass, and that's actually the point that the Earth orbits. That also means that technically the sun orbits that point as well, which just makes the sun wobble slightly. Now, the sun wobbles more dramatically from the larger pole, like the pole from the planet Jupiter, but it's still just a wobble, all right? But if you had two, say, equal mass stars, like star 1 and star 2, well, then they're actually going to orbit each other, essentially. They will orbit a shared midpoint that's exactly halfway between them, assuming that they have, in fact, identical masses. So it's really fascinating. There's lots of binary systems, which are two-star systems, where the two stars do orbit a shared center of mass, which doesn't have anything there. There's no actual mass located at the center of mass, but they both orbit around it. Right? Another example would be, a star that's twice as massive as another, again, having the center of mass nowhere particularly near either star, but of course more closer to the more massive star. And in the case of a planet, like a planet that is, in this case, just 1,000th as massive as the star, we see that the center of mass is within the star, but that creates the wobble that I mentioned. All right, so Newton Kepler's third law. So continuing with that particular refinement, right, that innovation of the universal law of gravitation, it went something like this. So Newton's laws of gravity and motion showed that the relationship between the orbital period, which you might remember from Kepler's third law, and the average orbital distance, a, which also sometimes more accurately is expressed as the semi-major axis of the elliptical orbit, but regardless, right, these two quantities, of a system tells us the total mass of the system. Because nowhere in Kepler's laws did he say that. He just said that p squared equals a cubed as a formula with not really traditional units, as long as p was in Earth years, so p was in Earth years, and a was in astronomical units, which was just Earth's average orbital distance around the sun. That was it. And it was just a sort of just say, okay, well, there's a ratio here, and all the planets follow the same ratio, okay? But that ratio between an Earth year and astronomical unit certainly can't hold for moons around Jupiter, so there has to be a new ratio between period and orbital distances. And that new ratio, as it turns out, is different for every system because it's always based on the mass of the system. So that means it's a way to solve for the mass of the system. So in other words, if you measure the period and orbital distance of a moon around a planet, you can calculate the mass of that planet. All right, so here's an example. Earth's orbital period of 1 year and average distance of 1 AU tells us the sun's mass. Right? That's one way to calculate it. There's other independent measurements that have confirmed it works, but this is one way that scientists calculate the mass of the sun. Pretty cool. The orbital period and distance of a satellite from Earth tells us Earth's mass. The orbital period and distance of a moon of Jupiter tells us Jupiter's mass. All right, as I said. Right, here is the formula. All right, so we have p squared equals 4 pi squared times a cubed over that constant I mentioned, the gravitational constant g, times the product of m1 and m2. All right, so I filled in all the missing parts there. Or you can solve for it as, let's see, let me check, yeah, like that. Or you can solve for it this way, where we have the product of m1 and m2, all right, and that's going to then equal, if you just rearrange things, 4 pi squared times a cubed over g times p squared. See? So there you have solved for the oh, it should be the sum of masses, not the product. My mistake. Okay, so this is the sum of masses. You might notice a moment ago I paused because I was unsure, but it absolutely is. And then I thought my original intuition was correct there for a minute, because of course in the original formula it is the product, but that at this point we've canceled out one of the masses in the derivation that we won't show you, that I won't show you. It's too much. It's not shown in the book. But going from the universal law of gravitation, which you recall from a couple slides back. Here, let me remind you. All right, so here it is. So the universal law of gravitation, right there, right? That law combined with Kepler's law is what gets us what's called Newton's synthesis of Kepler's third law, or Newton's version of Kepler's third law, right? But whatever you want to call it, this is it right here. But the important thing is it is a plus, all right? And then the G is outside of it, so we should put parentheses around it. All right, so there. All right. And the importance of this is it lets us solve for the mass, okay? Now, I kept saying that, in the previous slide did as well, that this formula lets you solve for the mass of the sun, the mass of Jupiter, the mass of the Earth. In each case, it was the object that was being orbited, right? But here we're seeing that it would be the mass of the sun, that's m1, plus the mass of the Earth. So technically, you're actually solving for both masses. It's the sum of the object masses. And again, all you need to know is the orbital period and the average distance, because pi is just a constant, and so is g, okay? But what's interesting is that since it's the sum of the masses, but one mass is so much bigger, you can approximately say that m1 plus m2 is just m1, as long as m1 is something like a sun compared to a planet, okay? So what determines the strength of gravity, right? Let's recap what we've learned. Well, it's the direct proportionality to the product of the masses and the inverse proportionality to the square of the separation. That's where it comes from, okay? Now, how does Newton's law of gravity allow us to extend Kepler's laws? Well, we realize it applies to other objects, not just planets, right? So we got all asteroids orbiting other asteroids, all kinds of examples. And it includes unbound orbits as well, right? That's a refinement. And it can be used with the formula we saw to measure the mass of orbiting systems, okay? Now, made a big deal. You can plug in the numbers, plug in P, plug in A, right? You have to, by the way, put these in base units if you're going to use this formula. So you wouldn't want to plug them in using astronomical units, certainly not Earth years. And the reason is because the units of the constant here are going to be in base units. And I just wanted to make that clear, so that's why I went back. Now, that means that the period would have to be in seconds. Often you're going to be converting a longer period, like days, into seconds. And the average orbital distance needs to be in meters, okay? Not even kilometers, but meters. And that's because the gravitational constant is 6.67 times 10 to the negative 11. It's a small number, right? And the units, by the way, are newtons meters squared over kilogram squared. All right, but since that constant is in those units, you have to be beholden to those units and make sure you convert. Okay, but then you can really find approximately the mass of whatever object is being orbited. Okay, so let's talk more about applications of gravity in our final section of the chapter, talking about orbits, tides, and the acceleration of gravity. Our questions that we want to answer are: how do gravity and energy allow us to understand orbits? How does gravity cause tides? And why do all objects fall at the same rate, right? Because we took for granted, didn't we? Right? And I said we'd come back to it. On Earth, remember, it was 9.80 meters per second squared, and that was everything, feathers to bowling balls. In the absence of air resistance, why though? Do you see it now with the universal law? Maybe. All right, so more about orbits, right? So total orbital energy, gravitational plus kinetic, stays constant, okay? Because there's no external force, that means angular momentum is conserved, right? And the energy is conserved because there's no energy leaving or entering the system, okay? Orbits cannot change spontaneously, simply, right? Orbits will only change if there is some other force, some other energy brought in. It doesn't happen that often, right? Planets don't happen to bump into each other, right? But you can change an orbit, right? Examples include the orbits of comets that spend millions of years at the very edge of the solar system and then might get perturbed, so have that very small orbit that they have turned into a long orbit that takes them closer to the sun, where then they interact with something like a massive planet like Jupiter that then takes what would have been a huge elliptical orbit and turns it into a much smaller elliptical orbit. So that's an example of a gravitational counter causing a change in the orbit of a comet. And this does happen throughout the years of the solar system, throughout the millions of years of the solar system. It's definitely a phenomenon. Sometimes even the incoming comet can get into an orbit not around the sun, but around the planet that it interacted with. So a planet can essentially gravitationally catch a planet or an asteroid or a comet or an asteroid. Okay. And sometimes friction or atmospheric drag can have a significant change because that would be an external force. That would be energy leaving the orbital system, getting turned into heat. Okay. So, as far as this energy idea and changing orbits, we can create orbits, obviously. We launch objects up and we put them into orbit, giving them enough energy to have an orbit. Because if you recall, having an orbit is just free fall, but it does require that you're moving really fast to the side, right? So you're falling down, yes, but you're moving so fast to the side you never hit the ground. And the number I gave you a while back was around 7,000 meters per second. Well, it takes a lot of energy to get to having an object moving at 7,000 meters per second. Its kinetic energy is large. That's why rockets have to have so much energy and they're so expensive. Okay, but beyond just the velocity need to go into orbit, there's something called escape velocity, and this is enough velocity to completely leave the gravitational potential energy of Earth. Okay, essentially, gravitational potential energy can be thought of as like being in a well, right? You're at the bottom of a well, and if you jump high enough or you jump with enough force, then you can jump out of that well. Well, if you give a rocket enough force, enough kinetic energy, it will leave the well, the gravitational potential energy well of Earth. Okay? And the escape velocity is faster than orbital velocities, as you would expect, and it's about 11,000 meters per second or 11 kilometers per second. Now, gravity definitely causes tides. Okay, clearly that's the cause. It's with the moon. It's related to the moon's gravitational pull on Earth as a whole, but then that affects fluids differently. So the moon's gravity pulls harder on the near side of Earth than on the far side. That's simply because we saw there's a strong correlation between distance, right? We have that 1/r² relationship between force from gravity and distance. Okay. Now, the difference in the moon's gravitational pull stretches out the Earth ever so slightly. The sun also has a small tidal effect on Earth. So that means that if the sun is pulling in the same direction as the moon, then tides are going to be higher because those two forces are in agreement. If the forces are perpendicular to each other, well, now they're not in agreement at all. And so what you're going to get is a situation where the tides are not as high. Now, interestingly, you can also have the sun and the moon on opposite sides, where you might think the forces again would not be in agreement or canceling each other out, but there's actually two tides for the pull. So even though the moon pulls most on one side, it causes a tide both on the near side and the far side, which has to do with just the fluid nature that comes after the consequence of the pull, right? So fluids behave different than solids. We're not just stretching things out, we're creating a force situation where fluids start flowing, and then there's a continuous effect, almost a domino effect of all those water molecules moving over the Earth as a whole. Okay, so tidal friction also gradually slows Earth down, because imagine that water gets moved around, right? Because of the outside force of gravity. But what happens is that water has its own inertia. That means that it's going to be moving as Earth is rotating. So that means that it kind of tugs back on the moon. Think force pairs from Newton's third law. Okay, so let's look at this figure, because it's actually a complicated idea, at least at first blush, but then it can sink in and make a lot of sense. So if you think about it, what happens is the moon pulls on, well, Earth. So the moon's gravity tries to pull on Earth. Okay, so that's going to create a tide. However, as the Earth rotates, the tidal bulges move with the Earth. As I said, they don't stay on the line that connects the Earth to the moon. And then friction with the rotating Earth pulls the tidal bulges along that path. Well, then what happens is the moon then tries to pull back on those bulges, okay, while the bulges pull on the moon. So two things are happening, right? The bulges are pulling the moon ahead, right, which will increase its orbital distance, and the moon is pulling back on the tides, which slows Earth down. So gradually, the moon is getting further and further away from Earth, and gradually, the length of our sidereal day is getting longer and longer. And over hundreds of millions of years, it actually is quite dramatic. Earth will have a much longer day in a few hundred years, a few 100 million years, not 100 years, and the moon will be much further away in a few 100 million years. Okay? And a few 100 million years ago, the moon once orbited faster than it did now, all right? And tidal friction caused it to lock into its current synchronous rotation. And that's why we know that only one face of the moon ever faces us, okay? So we can then go back to some laws and figure out why everything accelerates at the same rate. And what's pretty neat about finally being able to answer this question is that we're going to be combining the universal law of gravitation, the last of the big laws of physics that we saw in this chapter, with one of the earlier laws we saw, none other than Newton's second law of motion. So we take those two laws together, and that will show that everything on the surface of any planet will accelerate down at the same rate. Okay, the rate that happens to be numerically 9.80 meters per second squared on Earth. Okay, so here's the idea. Remember Newton's second law. It says the acceleration of a rock equals the force of gravity divided by the mass of that rock. Furthermore, the universal law of gravity says that the force of gravity equals big G, just that constant, times the product of the masses over the radius of Earth squared. Oh, well, check it out. That variable for the force of gravity shows up in both equations, both in the universal law of gravity equation on the right and Newton's second law of motion on the left. Well, then we can simply solve for Fg from both sides and cancel out the mass of the rock. See? Isn't that neat? The mass of the rock actually cancels out when we solve for the acceleration right there. And so even more than solving for Fg, what you should think of mathematically doing is what's called a substitution. So taking this value of F, which equals this larger expression here, right, the product and the constant divided by r squared, and actually inserting an n, and then just rewriting it. And that's actually all we've done here on the next line. And that immediately will put in the M rock term, any object, could be person, right? Anything, feather, bowling ball, in the numerator, and there's already an M rock term in the denominator, and indeed, that's how they cancel. So check it out. There we have an acceleration of the rock that's completely independent of the rock itself. Its own mass now no longer shows up. That means we could use this equation for any old object, and we'll always get the same number. Universal constant G, mass of the Earth, divided by the radius of the Earth squared. And when you put in the particular numbers for the Earth, then you get none other than 9.80 meters per second squared. You just put, the mass of the Earth, we put in about 9 times 10 to the 24 kilograms. You put in the radius at about 6.0, or 6.3 really, sorry for the messiness, times 10 to the 6 meters. Put in that constant, for G, 6.67 times 10 to the negative 11. I know it's chicken scratch. These are the numbers. You can look them up. And there you go. It's what you're going to get right out of it is 9.80. That's where it comes from, right? That's why everything accelerates at the same rate. Discovered back in the 1500s, understood well today, okay? Final thought question for you. Consider two objects being dropped from 1 meter above the surface of the moon, a hammer and a feather. Are the following true or false? All right, so you want to answer each of them true or false, 1, 2, and 3. All right, 1, the force due to gravity on the hammer and the feather are equal. Okay, the acceleration of the hammer and the feather are equal, and the mass of the hammer and the feather are equal. Okay, all right. So which of those are true? All right. Well, the force is not. Now we made a big deal about the acceleration being independent of the mass of the object, but we never said the force was independent. We just said the acceleration, and that definitely makes number two, true. They both accelerate at the same rate. Now, the number that happens to be based on the mass and radius of the moon about 1/6 of the acceleration on Earth. So whatever 1/6 of 10 is, okay? About 1.5 or something, right? And their mass is definitely not the same. Remember, mass is unique to objects. But again, to recap, the force not being the same, that's because, look, check it out. The force formula definitely is dependent on mass. So it's actually interesting. Although we're used to everything falling at the same rate, that also means that everything gets tugged a different amount. So the gravity that you feel is not the same force of gravity that someone else feels. We all fall at the same rate, but we all get pulled with an amount that is exactly proportional to our mass. All right? All because of this idea that mass universally attracts mass. So, what have we learned here in this final section? Well, we've answered the question, how do gravity and energy allow us to understand orbits? Because we know that in an orbit where nothing is being subjected to the orbit, nothing is entering it, nothing is encountering it, energy doesn't change and it doesn't enter or leave the system. So that conservation of energy means that the orbit doesn't change. But if you do change the total orbit, then the orbit will change, right? And you can change it with friction or another gravitational potential energy source, right? And if you add enough energy to some object, it will escape the gravitational pull. You can escape Earth's gravitational pull. You can even escape the sun's gravitational pull with enough velocity. In other words, enough kinetic energy. We also answered the question, how does gravity cause tides? It's the moon's gravity that stretches Earth and its oceans. And finally, we answered the question, why do all objects fall at the same rate? And it's because the mass of objects in Newton's second law exactly cancels mass in the law of gravitation. How cool. All right, well, I hope this last lecture and all of chapter 4 has been interesting and informative. Thank you for watching these videos.